Hello my friends and welcome back to the You Can Do TV channel.
Press processing is a manufacturing technology in which high compressive force is applied to metal materials, scrap, or forming stock to alter their shape and significantly reduce volume. It is widely used in both the manufacturing and recycling industries. The primary objectives are material densification, improved transportation efficiency, and better suitability for downstream processes. At the core of this process is the hydraulic press. Using hydraulic pressure generated inside large cylinders, the system can stably deliver forces ranging from several tens to several thousands of tons. Metal sheets, aluminum scrap, steel components, and cans are compressed into blocks or standardized shapes. The compression is carried out in a controlled, step-by-step manner, with optimal stroke length and holding time precisely set according to the material's mechanical properties. A key advantage of press, compression, processing is that it does not involve shearing or cutting, resulting in minimal material loss and limited damage to the internal structure of the material. In recycling applications, bulky mixed metal scrap can be compacted into high-density bales, significantly reducing storage space requirements and lowering logistics and transportation costs. Modern press systems integrate automatic feeding mechanisms, material detection sensors, and pressure feedback control, ensuring consistent quality and high repeatability. These advanced controls allow stable operation even with variable input materials. The compressed products exhibit high-dimensional accuracy, making them well-suited for subsequent processes such as melting, re-rolling, or reforming. In summary, press compression processing is a fundamental technology that combines high efficiency, operational reliability, and reduced environmental impact. It plays an essential role in metal processing and resource circulation, supporting both industrial production and sustainable recycling systems. The end product is a dense, cube-shaped metal bale with uniform geometry. This form is ideal for stacking, storage, and transportation, and it significantly improves handling efficiency in downstream processes such as shredding, separation, or melting. At a modern automobile recycling facility, the end-of-life journey of a vehicle begins in a controlled and highly mechanized environment. Whole cars are delivered to the yard, where they are prepared for shredding, a critical step in recovering valuable metals and materials efficiently. The Cinnebogan 835E material handler, equipped with a Liebherr hydraulic grapple, plays a central role in this process. Operators use the grapple to carefully lift and position entire vehicles onto a heavy-duty conveyor system. This conveyor transports the cars toward the shredder, often referred to as the, quote, final doom, a massive machine designed to break vehicles down into manageable fragments. The grapple allows precise handling, minimizing jams, and ensuring continuous operation of the recycling line. Before feeding the cars into the shredder, hazardous components such as batteries, fuel, and refrigerants are removed to ensure safety and prevent contamination. Any fluids that remain in the car are drained, and materials like tires and glass are separated for proper processing or recycling. Once the cars reach the shredder, enormous rotating knives and hammers pulverize the vehicle into small pieces. This initial size reduction exposes ferrous metals like steel and non-ferrous metals such as aluminum and copper for further sorting. After shredding, the material passes through advanced separation systems. Magnets extract ferrous metals, while eddy current separators isolate non-ferrous metals, which are then collected for smelting and refining. Remaining plastics, glass, and rubber are further processed or repurposed for other industrial applications. This ensures that nearly every part of the car is diverted from landfill and reincorporated into the manufacturing cycle. It's fascinating to think that parts of a car you see every day, like copper wiring, aluminum panels, or even small stainless steel components, may have originated from a vehicle long gone. From automobiles to raw materials for new products, the recycling process transforms end-of-life cars into high-value resources. In some cases, even tiny items like your nail clippers or electronics may contain metals that once traveled the roads inside a car. The journey from vehicle to raw material is a remarkable example of industrial efficiency, environmental responsibility, and the circular economy in action. At the heart of many heavy-duty recycling operations is the M&J Pre-Shred 4000 series shredder, a powerful industrial machine built to handle some of the most challenging waste streams, including whole vehicles and bulky scrap. Manufactured by M&J Recycling of Denmark, these shredders form part of a global range of mobile and stationary pre-shredding solutions used in waste processing and materials recovery plants worldwide. The M&J 4000M model, in particular, combines high capacity and versatility with rugged construction and advanced shredding technology. It is typically powered by a high-torque diesel hydraulic module and can process material at rates of up to 30,100 tons per hour, depending on feed size, density, knife configuration, and application conditions. The machine's large cutting table and twin-shaft rotor system allow it to handle a wide variety of input types, ranging from bulky industrial waste and construction debris to automotive scrap and appliances, without requiring extensive pre-sorting. A key feature of the 4000M design is its bidirectional knife assembly. The heavy-duty shafts, equipped with aggressive knives made from wear-resistant steel, rotate in both directions to maintain continuous material movement and prevent bridging. This mechanism enables the shredder to self-feed material and adapt automatically to variable input conditions without frequent manual intervention. Because of its open cutting table and robust frame, the M&J 4000M resists wear even when processing difficult or mixed waste that may contain metal, stone, or concrete. Components, such as bearings and wear parts, are positioned for easy access, simplifying maintenance and minimizing downtime. The design also allows the unit to be mounted on either tracked undercarriages or trailers, enhancing flexibility by enabling relocation between different sites or areas of a plant as needed. When a whole car is fed into an M&J 4000M shredder, the machine's powerful twin shafts tear the structure apart, reducing the vehicle to fragmented pieces suitable for downstream separation. These shredded fractions can then be sorted into steel, non-ferrous metals, plastics, and other materials for further processing, refining, and reuse. This capability makes the M&J 4000 series a cornerstone of modern recycling operations, transforming bulky, heterogeneous waste into manageable, valuable raw materials that re-enter industrial supply chains. At the world's largest copper recycling facility in Lunen, near Dortmund, electronic waste begins a new life. Every year, Germany generates nearly 1 million tons of discarded electrical and electronic equipment. Instead of ending up in landfill, this material is processed here with industrial precision to recover valuable raw materials. The process starts with safety. Hazardous components such as batteries and capacitors are removed before recycling begins. What remains may look like scrap, but it contains significant value. Printed circuit boards are especially important as they are rich in copper and precious metals. From just 1 ton of computer scrap, large amounts of copper, silver, and even gold can be recovered. Metal housings made of steel and aluminum are also separated for reuse. Next comes mechanical processing. Complete devices are transported by conveyor belt into a high-performance shredder. Inside, powerful rotating tools reduce the material into smaller fragments. This size reduction is essential, as it allows the different materials to be separated efficiently in the next stages. A sophisticated sorting system follows. Strong magnets remove all ferrous metals first. The remaining material passes through several separation stages, where plastics, aluminum, and non-ferrous metals are isolated. Air separation systems extract lightweight aluminum, while finely processed fractions rich in copper and precious metals are concentrated for metallurgical treatment. The copper-rich material is then transferred to the smelting plant. Here, it is melted together with industrial copper residues in large furnaces. The smelting process lasts around 8 hours and reaches temperatures of more than 200 degrees Celsius. The molten copper is then cast into large anode plates, still glowing with heat. To achieve the highest purity, the anodes undergo electrolytic refining. Suspended in acid-filled tanks, the copper is dissolved and redeposited onto stainless steel cathodes using electric current. Over several weeks, ultra-pure copper forms layer by layer. The result is copper with a purity of up to 99.995%. What was once electronic waste is now a high-quality raw material, ready to be used again in cables, pipes, and electronic components, completing the cycle of modern resource recovery.
The Nouvelle Route du Littoral is a 12.5-kilometer coastal infrastructure project designed to replace the aging, weather-sensitive existing road between Saint-Denis and the airport. The alignment comprises 2 major viaducts and multiple causeways, elevated above the ocean to withstand cyclonic and heavy rainfall conditions. The main viaducts use pre-stressed concrete segments, with span lengths up to 240 meters and widths of 30 meters. Supporting dual carriageways, a bus lane, and a cycle path. Construction relies heavily on prefabrication. Pile elements and voussoirs are cast in dedicated port-based factories under controlled conditions, allowing precise reinforcement placement and variable segment heights, from 3.8 to 7 meters to match the curvature and slope of the viaduct. Segments are transported via a specialized barge, Zourite, capable of lifting 5,000 tons and stabilizing offshore for accurate positioning. The embankments and protective dikes employ interlocking acropodes to absorb wave energy while reducing stress on the underlying structure. Installation utilizes POSI-block systems, allowing underwater placement without divers. Environmental monitoring includes hydrophones for underwater noise, turbidity sensors, and bubble curtains to mitigate impacts on marine life. Construction progress integrates rigorous quality control at each stage: segment fabrication, transport, positioning, and structural assembly. The project emphasizes safety, durability, and resilience against extreme meteorological events, aiming for full operational readiness by 2020.
Zenardi Fonderie continues its centuries-old iron casting tradition with modern technology and automation. This part of the journey explores the melting, treatment, and casting processes within their facility, a leader in ductile iron component production for industrial sectors. The foundry operates 3 network-frequency electric induction furnaces, each with a capacity of 28 tons and a power of 3,300 kilowatts. Furnaces are loaded with scrap steel, cast iron returns, and pig iron using vibrating loading cars and electromagnets. Once heated, molten base iron is extracted from the front via tilting. To achieve the desired chemical composition, operators add graphite, silicon carbide, ferrosilicon, copper, ferromanganese, and ferromolybdenum. Samples are taken for thermal and chemical analysis to monitor composition and temperature, essential for ensuring process stability. After melting, molten iron is transferred into a 3,000 kilogram treatment ladle, where spheroidization takes place through the addition of ferrosilicon magnesium alloys. This violent reaction transforms graphite into spheroidal nodules, improving mechanical properties. The ladle then passes through a secondary cleaning stage to remove slag before the final casting step. Before pouring into molds, a process known as inoculation is performed. Pre-inoculation introduces ferrosilicon alloys that serve as nucleation points for graphite nodules, preventing cementite formation and enhancing structural uniformity. A second post-inoculation is done just before the mold is filled, improving nodule consistency. Casting is controlled by an automatic pouring system using a sealed ladle, with nitrogen pressurization and a stopper valve to regulate the molten iron flow. Throughout casting, the operator monitors flow rate, temperature, and inoculant dosage via a control system with cameras and PLC software. Quality checks are continuously performed, including thermal analysis and metallographic tests to confirm graphite morphology and spheroidization effectiveness. Once casting is complete, molds proceed down the cooling line, allowing the iron to solidify. During cooling, carbon from the austenite phase migrates to graphite nodules, forming ferrite rings. If cooling is fast enough, it promotes the formation of perlite and bainite, enhancing strength. The mold is eventually broken, and the solidified casting or grappolo is extracted. The casting then enters a rotating drum, where water and movement remove remaining sand and cool the metal to room temperature. Operators perform primary shakeout, separating parts from runners and feeders. Components are sent to a shot blasting machine for final cleaning. Visual inspection and sample hardness testing are carried out, and usable parts are placed in metal crates for storage. Scrap returns to the raw material yard for recycling. Zanardi's process ensures metallurgical quality and efficiency through automation, precise alloying, and advanced thermal management, laying the foundation for final machining and finishing processes explored in future videos. Iron and steel, essential across industries, are highly vulnerable to corrosion. Marmara Seegener Galvaniz addresses this issue with a durable, cost-effective, and eco-friendly solution: hot dip galvanizing. The process begins with chemical cleaning, degreasing, acid pickling, rinsing, and flux coating, followed by immersion in a 450 degrees Celsius molten zinc bath. This creates a microns-thick zinc layer that protects against corrosion for up to 120 years. Galvanized products are cooled, inspected, and prepared for delivery without requiring post-treatment, reducing both maintenance and logistics costs. Marmara Seegener operates 3 advanced plants in Izmit, Gebze, and Korlu, strategically positioned across the Marmara region. These facilities feature zinc baths up to 16 meters in length and a combined annual capacity of over 160,000 tons. By combining German expertise from Seegener Holding with continuous investment in R&D and modern infrastructure, Marmara Seegener Galvaniz leads the sector in sustainable metal protection and high-value industrial service. Located on the northern edge of the Harz Mountains, Ilsenberger Groblech GmbH stands as a key pillar in Europe's heavy plate production industry. Supplied by the Integrated Steelworks in Salzgitter, which produces over 4 million tons of steel annually, the plant receives high-quality slabs via rail for further processing. These slabs undergo rigorous inspection before entering the hot rolling program, starting with laser-measured sizing and weighing, followed by heating in natural gas-fired pusher furnaces. After 4 hours of controlled heating, slabs are transferred to the rolling mill, where powerful hydraulic and electromechanical systems apply forces up to 8,000 tons. The 2 by 6,400 kilowatts drive powers work rolls supported by backup rolls, achieving thickness tolerances of plus or minus 0.5 millimeters across widths of 800 to 3,500 millimeters. Descaling spray systems operating at 200 bars clean the slab surfaces before rolling. Automated rolling schedules consider slab temperature, steel composition, and desired final dimensions. Following hot rolling, accelerated water cooling is employed to tailor mechanical properties, all managed through a central automated system. After cooling, plates undergo ultrasonic testing for internal defects, then marking, trimming, and sample extraction for mechanical and impact testing. Ilsenberger operates a sophisticated testing laboratory featuring CNC machines and low-temperature impact testing down to -196 degrees Celsius. Spectrometry, thermal analysis, and electron microscopy confirm alloy composition and microstructure quality. The production range includes normalized, annealed, or quenched and tempered plates, with water quenching units ensuring consistent strength and toughness. Ilsenberger also offers surface conservation, edge milling, and precision cold straightening. Quality control is rigorous, with tensile and impact testing conducted under controlled conditions, including extreme temperatures. Additional analysis using spectrometers, optical microscopes, and scanning electron microscopy ensures internal microstructural integrity. Certified under ISO 9001 and supported by numerous approvals, with an output of approximately 17,000 plates monthly, Ilsenberger serves sectors such as bridge and crane construction, shipbuilding, pipelines, and wind turbine towers. Notably, it has supplied steel for nearly 5,000 wind turbines, contributing to 9,000 megawatts of renewable energy capacity. As one of Europe's leading manufacturers of quarto plate, Ilsenberger Groblex GmbH combines advanced rolling technology, comprehensive quality control, and customized steel solutions to meet the highest industry demands across global markets. Timber crown gear forging is a multi-step hot forging process used to produce high-strength gears with precise geometries. The process begins by heating the metal billet to forging temperature, then transferring it to a flattening station, where it is compressed to achieve a uniform thickness and improve the internal grain structure. Next, the billet is punched with a central hole, which is precisely punched using a die and high-pressure punching system. This hole serves as a reference point for further processing. The forged billet is then transferred to a flange-forming machine, where specialized dies shape the outer diameter and flange contour. This station ensures dimensional accuracy and surface alignment. Throughout the forging stages, temperature and strain rate are tightly controlled to prevent defects such as cracking or warping, ensuring the mechanical integrity and accuracy of the finished gear. The forging process begins with the selection of high-quality raw materials that meet precise specifications. These materials are heated to extremely high temperatures, typically between 1,100 degrees Celsius and 1,250 degrees Celsius, to achieve optimal malleability. Once heated, the metal is transferred to forging presses or hammers where it is shaped under immense pressure into the desired form. Modern forging plants use advanced equipment such as hydraulic presses, mechanical hammers, and automated robotic systems to ensure precision and efficiency. After forging, components undergo trimming, heat treatment, and surface finishing processes. The forged components are allowed to cool naturally at room temperature after shaping. This natural cooling process helps to relieve internal stresses and improve the metal's structural integrity before further processing such as heat treatment or machining.
The VB1500DK is a heavy-duty tire handling and processing system designed for large OTR tires used in mining and construction equipment. Built on a robust tracked platform, the unit provides high mobility across rough terrain and delivers powerful, controlled handling for tires weighing up to 1.5 tons. Its hydraulic clamping arms offer variable gripping force, ensuring secure manipulation without deforming the sidewalls. Full rotation and tilt functions allow precise alignment during mounting, demounting, or positioning operations. In tire recycling applications, the VB1500DK is frequently paired with Hamel's industrial shredding technology. Massive OTR tires, normally extremely difficult to process due to their steel-reinforced structure, are fed into the shredder using the VB1500DK's controlled hydraulic arms. The machine stabilizes the tire, positions it correctly, and assists in continuous safe feeding. Once engaged, Hamel's dual-shaft shredder rips through the rubber carcass, steel belts, and bead bundles, reducing the tire into uniform, recyclable fractions. The VB1500DK ensures steady loading, eliminates uncontrolled movements, and enhances operator safety by keeping personnel away from the shredding zone. Together, the VB1500DK and Hamel's shredder deliver a fully integrated high-performance solution for OTR tire handling, removal, and industrial recycling. Shredding through the toughest materials with relentless force, the RG's 250 Impactor redefines mobile recycling with its compact power and unmatched versatility. In this sequence, the machine takes on a formidable task: the reduction of massive off-road tires, often weighing several hundred kilograms, and constructed with reinforced steel belts. The Impactor 250 is equipped with a dual-shaft shredder system driven by a 220 horsepower Volvo diesel engine. Its slow-speed, high-torque design ensures a powerful bite, gripping and tearing through dense rubber, steel bead rings, and layered sidewalls. The hydraulic system automatically adjusts torque to material resistance, preventing blockages while maximizing throughput. Mounted on a track chassis for mobility in rugged environments, the unit features an interchangeable shaft system, allowing users to adapt tools depending on the application, from tires and concrete to C&D waste and wood. For tire shredding, the special shafts are profiled to aggressively penetrate and slice each section with rotational shearing force. The operation starts with the massive tire being manually loaded into the feed hopper. As the shafts engage, the material is drawn inward and fragmented into fist-sized chunks, small enough for downstream processing or further granulation. Reinforced steel cords are twisted and separated during the cutting, demonstrating the machine's ability to dismantle composite waste streams with precision. The shredded material is discharged through the hydraulic discharge conveyor system, an integral part of the RG's Impactor 250's design. Once the tire is broken down into uniformly sized fragments by the shredding shafts, the discharge conveyor continuously transports the processed material away from the shredding chamber, ensuring uninterrupted workflow. Compact, efficient, and designed for demanding job sites, the RG's Impactor 250 delivers outstanding performance in tire recycling, transforming industrial waste into manageable, recyclable fractions in real time. Bales. The car tire shredding sequence unfolds with a mix of power and raw mechanical drama. As each worn tire is placed onto the in-feed conveyor, it begins its final journey, rumbling forward toward the shredder's counter-rotating shafts. The moment the hardened knives bite into the rubber, a deep, resonant crack echoes through the chamber. Rubber, steel belts, and fabric layers giving way under relentless torque. Bit by bit, the tire is pulled apart, transformed from a solid ring into flying fragments. The pieces fall through the sizing screen, where magnets sweep away steel strands, leaving clean rubber chips ready for a new life. It is a striking blend of destruction and renewal, turning discarded tires into valuable resources. The Rex 7242 hydraulic tire baler is engineered to consolidate waste tires into dense, uniform bales measuring approximately 72 inches wide, 42 inches deep, and 48 inches high. The cycle begins by stacking tires evenly inside the compression chamber, placing special attention on seating each tire into the corners to create a stable, interlocked pack. As the chamber fills, the operator closes the loading door to maintain containment while continuing to feed additional tires. Once the chamber reaches capacity, the hydraulic system is activated, driving the ram downward to apply high compaction pressure. The baler allows intermittent loading during compression, ensuring the full tire batch is captured in a single cycle. After all material is compacted, the ram is driven fully to the bottom stop, and the operator inspects each wire slot to ensure it is unobstructed. Retainer dogs are lifted and pinned to prevent engagement during ejection. With the chamber stabilized, the front door is manually opened from a safe lateral position. Strapping or baling wire is threaded through the designated slots to secure the compressed tire block. The rear ejector chains are then connected, and with all safety positions verified, the ejector is activated to discharge the completed bale from the machine. In this powerful demonstration, CM Shredders showcases the capabilities of its H50 hybrid dual-shaft shredding system by processing large, industrial-grade sandpaper stamp rolls. These tightly wound rolls, made from abrasive materials, are difficult to handle, but the 50-horsepower H50 easily reduces them to manageable pieces. Designed for high-torque, low-speed operation, this shredder delivers reliable size reduction while minimizing noise, dust, and wear. The H50 Hybrid is built to tackle tough materials. Featuring CM's patented knife technology, first perfected in the extreme environment of tire shredding, this system offers unmatched durability and precision. The shredder's dual shafts rotate at optimized speeds to cut, tear, and shear material with minimal energy loss, reducing maintenance requirements and extending blade life. Knife configurations are available in various sizes, making the H50 adaptable to a wide range of materials beyond sandpaper, including plastic, rubber, and metals. This test not only highlights the shredder's efficiency, but also its role in sustainable waste management. By reducing the volume of bulky roll waste, the H50 makes transportation and recycling more economical. Less volume means fewer trips, lower emissions, and reduced landfill dependency. CM Shredders also designs complete turnkey systems that integrate ferrous and non-ferrous metal recovery. wood recycling, light/heavy material separation, and advanced material handling. Their solutions support a wide range of industrial applications with customized layouts and plug-and-play installations. In addition to its technical capabilities, the CMH50 hybrid shredder is designed for operator convenience and long-term reliability. The system features an external bearing design that protects critical components from contaminants, ensuring smoother operation and easier maintenance. A centralized lubrication system simplifies upkeep, reducing downtime and enhancing safety during servicing. The control panel includes intelligent monitoring for motor load and temperature, allowing for automatic adjustments during heavy-duty cycles. With a reputation built on strength, reliability, and innovation, CM Shredders continues to lead the field in recycling technology. The H50 hybrid system is a prime example of how engineered performance can improve operational efficiency while supporting environmental sustainability. Whether it's in a recycling center, industrial plant, or manufacturing facility, CM's shredding systems deliver proven performance today and into the future. In modern Bradford waste traders, end-of-life vehicles are processed using the Moros HP110 shear, a high-performance machine designed for efficient and safe scrap car dismantling. The process begins with the reception and inspection of incoming vehicles, ensuring that hazardous materials such as fluids, batteries, and airbags are safely removed prior to mechanical processing. Once the vehicles are cleared, they are positioned for the HP110 shear operation. The Moros HP110 is equipped with a hydraulically powered cutting system capable of handling large automotive steel structures. The machine applies precise shear force to cut through the car's frame, body panels, and engine components, reducing the vehicle into manageable scrap sections. Its robust hydraulic cylinders generate consistent pressure, ensuring clean cuts while minimizing strain on the machinery and maintaining operator safety. During operation, the HP110 shear allows for adjustable cutting angles and blade settings, optimizing the process for different vehicle types and thicknesses of metal. Components that contain non-ferrous metals, such as aluminum hoods or radiators, are separated for further sorting. The shear's integrated control system monitors hydraulic pressure, blade alignment, and cutting speed in real time, preventing overloads and ensuring operational reliability. After shearing, the compacted vehicle sections are transferred to storage or directly to the next stage of processing, which includes shredding, magnetic separation of ferrous metals, and non-ferrous sorting for recycling. The precision and efficiency of the Moros HP110 enable Bradford waste traders to process large volumes of scrap cars per shift, while maintaining consistent quality and throughput. This combination of advanced hydraulic shearing, real-time monitoring, and careful pre-processing ensures that each vehicle is dismantled safely, maximizing metal recovery and preparing materials for downstream recycling operations in compliance with environmental and industrial standards.
The Flex 1000 mobile drum by Panazzolo is a transportable hammermill system designed for efficient treatment of aluminum profiles and MSW cans. It offers a robust hourly production rate of 6 to 8 tons, making it ideal for high-volume material recovery operations. The plant integrates a magnetic drum separation system for ferrous materials and the SMNF 1000 Eddy current separator for non-ferrous sorting. Outputs are cleanly divided into aluminium profiles, magnetic materials, and plastic/rubber fractions. Powered by an energy-saving motor, 250-315 kilowatts, the system ensures strong performance with reduced power consumption. Built for field flexibility, the entire setup is engineered for quick transport and rapid deployment. Its modular, user-friendly design also emphasizes fast and easy maintenance, reducing downtime. The Flex 1000 is a compact, mobile solution for sustainable processing of recyclable metals and waste, enhancing productivity in scrap and recycling industries.
A mixed aluminium scrap recycling plant is designed to efficiently process heterogeneous aluminium waste streams into high-quality secondary aluminium suitable for remelting and manufacturing. The process begins with the reception of mixed scrap, which may include cast aluminium, extrusions, profiles, sheets, and contaminated components from industrial, automotive, and post-consumer sources. Incoming aluminium scrap is first handled by multi-tine grapple cranes, which are designed to efficiently lift, sort, and feed irregular and bulky scrap into the processing line. These machines ensure a controlled and continuous material flow, preventing overloads and protecting downstream equipment. The scrap is then transferred to a shredder or crusher, where size reduction takes place. Twin shaft or single shaft shredders are commonly used to break down large aluminium pieces, mix scrap, and compacted materials into manageable fragments. This process liberates aluminium from attached contaminants such as plastics, rubber, wood, and light steel components. For thicker or cast aluminium scrap, hammer mills are often employed, delivering high-impact crushing to achieve consistent particle size and improved material liberation. Further refinement is achieved through screening systems that classify material by size, followed by air separation units that remove light contaminants such as plastics, foils, dust, and insulation residues. The processed scrap is then compacted into bales or chips to optimize furnace charging efficiency. By combining mechanical, physical, and sensor-based separation technologies, a mixed aluminium scrap recycling plant maximizes metal recovery, minimizes waste, reduces energy consumption compared to primary aluminium production, and supports a closed-loop, sustainable aluminium supply chain. Scrap cars represent one of the most important material streams in the modern recycling industry, combining large volumes, complex material composition, and high recovery potential. An end-of-life vehicle is not waste, but a concentrated source of reusable metals and components that can be returned to industrial production through controlled processing. A typical scrap car consists primarily of steel, with significant quantities of aluminum, copper, and smaller amounts of plastics, rubber, and glass. Before any heavy processing begins, scrap cars are collected, registered, and prepared for recycling. This preparation stage focuses on safety and environmental protection, ensuring that hazardous elements are managed correctly. Once depolluted, the vehicle enters dismantling operations. Reusable or high-value components such as engines, gearboxes, catalytic converters, starters, alternators, and electronic modules are removed. Tires, glass, wiring harnesses, and interior materials are separated to improve the purity of subsequent material streams and to enable specialized recycling routes. The remaining vehicle body is then processed mechanically. Hydraulic balers compress the car into dense blocks, or the shell is fed directly into a shredder. The compression sequence is carried out in stages. First, the roof and sides are collapsed to remove voids and trapped air. Next, longitudinal and vertical pressure is applied, folding the body structure inward. High-strength steel components deform plastically, while weaker elements flatten and interlock, creating a dense, uniform mass. Throughout the cycle, pressure and stroke length are precisely controlled to ensure consistent block dimensions. Within minutes, the original vehicle is transformed into a compact, cube-shaped bale with significantly increased density. This square block is easy to stack, store, and transport, dramatically improving logistics efficiency. The compressed form also optimizes downstream processing, allowing faster and more stable feeding into shredders or melting furnaces. Through this integrated process, scrap cars are transformed into high-quality secondary raw materials. This reduces the demand for virgin resources, lowers energy consumption, and significantly cuts carbon emissions. Scrap car recycling, therefore, plays a crucial role in supporting sustainable manufacturing and the circular economy.
The metal
Located
scrap loading operation utilizes a mobile loading machine, specifically designed for efficient container handling. This unit is fully mobile and can be deployed or set up on-site within approximately 10 minutes, offering rapid operational readiness. It is equipped with a high-capacity hydraulic arm and specialized gripping attachments that enable secure and precise handling of various types of metal scrap, including bulky or irregularly shaped pieces. During operation, the machine loads scrap directly into standard shipping containers, ensuring optimal fill density and minimizing the risk of damage to the container or material. The system is designed for continuous workflow, capable of loading approximately 20 containers per 10-hour shift, which equates to around 400 to 450 metric tons of scrap. Operators control the loading process from a cabin with clear visibility, while automated features assist in positioning, weight distribution, and material compaction to maximize container capacity. The mobile design allows flexibility in site layout, reducing downtime between shifts and improving overall productivity. Safety features, including emergency stop mechanisms, overload protection, and stabilized support legs, ensure secure operation in industrial scrapyard environments. This machine provides a highly efficient and technically reliable solution for large-scale metal scrap loading operations.
The pneumatic power hammer shown in the video is specifically engineered for efficient removal of foundry risers, casting heads, and feed heads from various castings. This specialized tool also functions effectively as a breaker for foundry shells. It is designed to detach risers, feeders, gates, and sprues from iron and steel alloy castings with precision, minimizing any risk of damage to the casting body. Compared to conventional methods such as sledgehammer blows or flame cutting, the wedging to gating hammer provides a safer, faster, and more environmentally friendly solution. The pneumatic mechanism delivers controlled impact force that reduces the likelihood of casting surface damage or cracks during the removal process. Additionally, Its user-friendly operation makes it a preferred choice among foundry workers, increasing overall efficiency and safety in casting cleaning operations. By improving productivity and maintaining casting integrity, the Weijing Foundry degating hammer represents an advanced technological tool in modern foundry processes.